I welcome you all to another tutorial video session on finite element procedure for solving structural engineering problem. My name is Ayodele Akinadamo. In today's video, we are going to solve a Truss system by elimination method by applying the finite element procedure. This is the Truss problem we are going to solve in this video. I've solved this problem in my previous my previous videos by two methods. In today's video, I'm going to solve this problem by elimination method. I'm going to deal with the boundary condition of this Truss system using the elimination method. I'm not going to explain like the whole step of analyzing this particular Truss problem because I've done this several times in my last two video tutorial session. So I highly recommend you go back to those videos for you to understand how to actually analyze Truss system using the finite element procedure. So I'm not going to explain this model again because I've done it several times, as I've said. The first thing we need to do when we are using the finite element procedure is we need to define our finite element model for the Truss. And this image here actually defines the finite element model, where I numbered my element, I number my nodes, I number my degree of freedom, and I also indicated the direction of each of my elements. So I highly recommend you go to my previous video on how to define the Truss finite element model. We are also told in the question that the cross-sectional area of all our elements is 20.7 times 10 raised minus 4 meters square, and the E, the Young modulus, is 205 times 10 raised 6 kilonewton per meter square, which is also equivalent to 205 gigapascal, 205 GPa. So we are using Matlab to solve this problem by elimination method. The only thing I'll show you about this elimination method is actually how to apply the elimination method to the global stiffness matrix. Assuming assuming our global stiffness matrix is defined by this 6 by 6 matrix you see, and assuming we have supports along degree of freedom 1, 3, and 7, 1, 3, and 5. It means that we have to knock off the elements in our global stiffness matrix along the rows and columns at degree of freedom 1, 3, and 5. So let's say this is our 6 by 6 matrix, and our numbering is 1, 2, 3, 4, 5, 6, 6 columns. The same thing for the row 1, 2, 3, 4, 5, 6. So because assuming we have support degree of freedom at 1, 3, and 5, it means that we will knock off all the values along the rows and columns in that direction. So you see that's why I drew a line along column 1, I drew a line along column 3, and I also drew a line along column 5 in the column direction. In the row direction, I also drew a line in the first row, I drew a line on the third row, and I drew a line on the fourth row. So when you have drawn this line, what are the values that remain? The values that remain is our modified global stiffness matrix. So that's how we modify the global stiffness matrix by using the elimination method. In this problem, after knocking off the rows and columns along degree of freedom 1, 3, and 5, this is actually what remains at 1, 3, and 5. So it will remain this element here, to remain this element here, this element here, same thing here, this element here, this element here, this element here. Also, it will along column 6, this element here, this element here, and this element here. So this 9 values I circled is our modified global stiffness matrix, which is what you actually see here. So I'm denoting mod K as my modified global stiffness matrix. So this is a matrix that you have to invert for you to get your displacement quantity. For you to get your displacement quantity for your for our Truss system. So this is actually what you need to know when you are using the elimination approach. I'm going to illustrate how we use the elimination approach on the Matlab working environment. So now, um, now we are going to move to the Matlab working environment where I will show you how to use the elimination method approach. So now we're in the Matlab working environment. This is actually the live script which I'm going to use to explain the elimination method approach to you. I'm going to upload this Matlab script on in the description section of under this YouTube video, so you can look at you can study this scripts to fully understand the elimination method using the finite element procedure. I'm not going to actually explain all the steps to solve this problem because I've already done the explanation in my previous video using penalty method, using two different methods, using the penalty methods. So the only part I'm going to explain is how we actually modify our global stiffness matrix. But the first thing you need to do, as I've said, you define your model. This is the defined model. So then after you have defined your model, your finite element model, the next step is to calculate or determine the local stiffness. This is not global. The local stiffness matrix of all the elements. So I've already explained this in my previous video. I explained how we compute the local stiffness matrix for all the 11 elements in our Truss system. So first you define the geometric property um, and the material property, which is this E is the Young modulus, A is the cross-sectional area, theta 1 is the angle of element 1, L1 is the length of element 1. So I use this function to actually define my local stiffness matrix. So when I run this, my local stiffness matrix for element 1 is formed. Also, the L1 here is representing my cosine angle. M1 is representing my sine angle. This code here returns 3 output variables, which is K1, L1, M1. L1 cos theta, M1 is sine theta. And our theta here is defined as 0. So that's why we have 1 and 0. So this is done for element 1, 2, 3 to element 11. So I strongly recommend you check my previous video for better explanation on how to calculate compute the local stiffness matrix for all the elements. So after we have defined our local stiffness matrix for all the elements, the next thing we need to do is to assemble our global stiffness matrix. And while we're doing that, we do this by first defining our what they call it, defining a base matrix. Our base matrix is a zero matrix, a blank matrix, and because for this Truss model we have 12 nodes. For this Truss model, we define a zero square matrix of size 12 by 12. So this function actually creates a zero square matrix of size 12 by 12. I'm defining my global stiffness matrix as K. So what we need to do, we need to add K1, K2, the local stiffness matrix for all the elements K1, K2 to K11 to this zero matrix. I explained this procedure in my previous video, so I strongly recommend you check those videos for better explanation. So you see now I added K11 finally to the zero matrix, and this is actually our final global stiffness matrix of size 12 by 12. It's a symmetric matrix in which you cannot invert it. So, but the only way we can manipulate this matrix is actually to modify it. That's why we are using our support degree of freedom by the elimination method. So this is our final 12 by 12 matrix. But because we are using the elimination method, we need to actually knock off the support degree of freedom in this 12 by 12 matrix. In our question, we have support at node 1 and node 4. And at node 1 and node 4, we have degree of freedom 1, 2, and 1, 2, 1, 2 at node 1, 7, 8 at node 4. So the degree of freedom are 1, 2, 7, 8. So along the rows and columns, we need to eliminate row 1, row 2, row 7, and row 8 along the row, and the same thing along the column. So what in the 12 by 12 global stiffness matrix, what we need to keep are only the rows and columns for the non-support degree of freedom. We need to knock off the degree of freedom at node 1 and at node 4. So that is just the elimination method. And we can use a simple Matlab line of code to actually knock them off. So I will show you how to actually do this now. So this is our 12 by 12 matrix, and we want to eliminate rows and columns at node 1, at row 1, row 2, row 2, row 7, and row 8, and also along the column 2 at row 1, at column 1, column 2, column 7, and column 8. So what we do, we don't want 1 and 2. We don't want 1 and 2, but we want 3 to 6. We don't want 7 and 8, but we want 10 to 9. This along the column. So this is, we want 3 to 6 and we want 9 to 12. So that's why I have 3 column 6. That's why I have 3 column 6 comma 9 column 12. This 3 column 6 means 3, 4, 5, 6. This 9 column 12 means it means 9, 10, 11, 12. So I'm extracting these rows and columns in the global stiffness matrix. So this is how you extract the values you need in the global stiffness matrix. You write this in square brackets, comma, you repeat the same thing in square bracket. So this is how you extract it. So we have eliminated 4 rows and 4 columns. So what will remain will be an 8 by 8 matrix. So this is our modified global stiffness matrix. When we run this code, this is our modified global stiffness matrix. So after we have formed our modified global stiffness matrix, which I gave a variable name mod k, the next thing is actually to define our force vector. And for this question, our force vector, I've already explained, is defined by this variable PS. It contains 12 values. It's a 12 by 1 column vector. It's a 12 by 1 column vector. I've already explained how I compute this in my previous video, so I highly recommend you go to my previous video on this. You can see there are only 3 forces on this truss element. That's why we have minus 500 here, minus 2000, and minus 1000 here. I'm working in newtons, so that's why this is 500, 2100. So for the force vector, we also need to modify the force vector. We need to knock off degree of freedom 1, 2, 7, 8. Currently, the PS is the 12 by 1 matrix. We need to reduce it to an 8 by 1 matrix where row 1, row 2, row 7, and 8 are eliminated. So the same thing with the modified global stiffness matrix. I only need elements between row 3 and 6, between row 3 and 6, that is 3, 4, 5, 6, and 9, 10, 11, 12. So that's, you write this in square bracket, comma 1. This one means column, the first column. It only has one column. You must specify it like this. So let this value be stored in a variable which I'm calling mod PS. This is my modified force vector, mod PS. So this is an 8 by 1 matrix. So these are modified force vector. So once we have done this, once we have determined our modified global stiffness matrix mod K and our modified force vector mod PS, we can multiply these two together to get our displacement vector for the truss. And this displacement vector will only give us the displacement at the non-support degree of freedom, where that's where we don't have support degree of freedom. So when we invert mod K, that is modified stiffness matrix, when we modify it, it's an 8 by 8 matrix. And when we invert mod K and multiply by the modified force vector, we get this quantity. 1, 2, 3, 4, 5, 6, 7, 8. But you should note that the first 4 are quantity at node 3, 4, 5, 6, while the next 4 are quantity for the displacement at node 9, 10, 11, 12. You should note this. So this is the displacement quantity for the for our truss system at the non-support degree of freedom. So if you want to like assemble like the global stiffness, you can simply say as in 0. We know that the displacement at our support degree of freedom is 0. So at position 1, I put 0. Like ds is representing my global displacement vector, as in the global, the 12 by 1 matrix, and we are assembling it together. So the degree of freedom 1, there is no movement there, so this is 0. Degree of freedom 2 is also 0 because we have support there. Then from 3 to 6, you can see that I extracted 1 to 4 in this position, 1 to 4. So that is why it is mod ds 1 colon 4 comma 1. So this is the displacement vector between 3 to 6. At 7, this was 7 and this was 8. We have support degree of freedom at 7 and 8. So that's why this is 0. And at the remaining from 9 to 12, we have 5 to 8 of this modified degree of freedom, 5 to 8. That's why this is 5 colon 8 comma 1. So once you run this code, you get your 12 by 1 matrix. So you see now we have our 0, 0, our displacement vector at 3 to 6, 0, 0, and our displacement vector at 9 to 12. This is how it is done on the Matlab environment. From here, you can say you want to start extracting your displacement vector for each element. Element 1 displacement vector, I'm denoting as ds1, element 2 ds2, in that order to element 11, ds11. So for element 1 is found between node 1 and node 2. Let me show you. I've already explained this in my previous video, but I'll show you again. Element 1, this element 1 is located between node 1 and 2. So because of that, the degree of freedom at node 1 and 2 are 1, 2, 3, 4. So our number will be 1 column 4. That is 1, 2, 3, 4. So that's why we have 1 column 4 when we're extracting the local displacement vector for element 1. That is at this point. We have 1 column 4. We have 1 column 4. So I am extracting one as in the first 4 elements in DS for DS1. I'm extracting the element input at position 3, 4, 5, 6 in DS for DS2. I'm extracting the elements, the values at 7 to 10, 7, 8, 9, 10 for element 3, because those are the degree of freedom at for element 3. So you do this for the 11th, for all the elements. calculate the local displacement vector for all the elements, which I've done. You should refer to my other video for more explanation on this. I don't want to waste time. I want to finish this video quickly. I don't want the video to be too lengthy. That's why I am going through it quickly. So this is how we apply elimination method to solve source problem on the Matlab working environment. Once you have calculated the displacement vector, you can calculate the axial force in the element, and it's very using this formula. This formula is the axial stress, where E is the Young modulus, L is the length of the element, this is a square bracket, this L is the cosine angle cos theta, this M is the sine angle sin theta at the start node. The Q is the displacement vector for each of the elements, which we define here as ds1, ds2 to ds11 for element 11. So this is the shear normal stress. Let's say you are not interested in normal stress and you are interested in the axial force. What you just need to do is to multiply this normal stress formula by the cross-sectional area. I've explained this in my previous video. You should refer to it. So I implemented this formula in all this Matlab line of code. I calculated the axial force for each element. F1 is the axial force for element 1, F2 is the axial force for element 2 to F11. So I got the axial force values using this formula. You can see using this formula. Please, I highly recommend you you refer to my other video for better explanation on how to actually use this formula. This is how we actually calculate the axial force using this formula. So these are AutoCAD drawing which I use to actually depict these axial force values. So you can see axial force F1 is minus 5.4634 times 10 power 3 Newton. That is you can also say minus 5.46 kilonewton. This is Newton, 10 power 3 kilonewton without the 10 power 3. And because it is negative, it is in, why I say compression, it is in compression. If it is positive, it is tension. So this is compression. This F1 is element 1 is a compression member with 5.46 kilonewton force. So that's what we have here, 5.46 kilonewton force. 5.46 kilonewton force in compression. Element 2 is also in compression, 0.94 kilonewton force. So this is how we do it. If we don't want to use this formula for the axial force, you can also use this formula. This formula is like the local force vector for the element is equals to the local stiffness matrix multiplied by the local stiffness vector. So we can use this. We already calculated K1 and displacement vector already. So we can calculate the force vector for each element. We have a 4x1 matrix where this is this is the first two is for the start node, while the second two is the forces on the end node. Like for element 1, in the x direction, the force is 5.46 kilonewton. In the vertical direction, it is 0. This is for the end node. The force in the x direction is minus 5.46 kilonewton. In the y direction, it is 0. So like that. For element 2, the same thing. The first two is for the start node, the second two is for the end node. So this is what we do for all elements, for the 11th element. So this is how we apply elimination method to solve source problem using the finite element approach. So now I've come to the end of this video. In my next video, we're going to use the ANSYS program to ANSYS is a finite element software. So I'm going to use the ANSYS program to actually model this Truss problem. We model the problem and we will compute the axial, the deflection at each node and the axial force in each element. We'll compare our results with our finite element calculation on Matlab in my next video. So my next video will be on the ANSYS working environment. So don't I wish I wish thank you so much for watching my video, and I hope you've learned one or two things about finite element procedure for solving source problem um, on Matlab. Uh, See you next time.